Hi, hello. For this video, we will be discussing another technique in solving DC electrical circuits, and this is called nodal analysis. Okay, so nodal analysis is based on a systematic application of our KCL, which is your Kirchhoff's current law. So nodal analysis allows us to obtain a set of simultaneous equations to solve for voltages and current in any linear circuit. So if you're going to remember our previous video, it is about mesh analysis, and that is based on our KVL. So this time, this is another approach, and we're going to apply what we have learned in Kirchhoff's current law to this nodal analysis method. Okay, so in nodal analysis, we are interested in finding the node voltage. Okay, so if in mesh analysis, we're interested in solving for the mesh currents, this time we will be trying to solve our node voltages. So this applies to circuits which has or wherein your unknowns are the node voltages instead of currents. Okay, so it says here in a given circuit with n number of nodes, we have first to set a reference node. Okay, so we're going to assign voltages VA, VB, VC depending on what nodes you're trying to solve, or we can also write that in terms of numbers. So we can write V1, V2, V3 corresponding to node number 1, node number 3, and node number 2, number 3, and so on. Okay, so to the remaining nodes. And then usually the number of nodes, nodal equations that we're going to form is equivalent to n minus 1, wherein n is the number of nodes. Why? Because why do we have minus 1? Because one node will be used as a reference node. So for example, we have 4 nodes in your circuit. We can have only up to 3 equations because the fourth node will be used as a reference node. Okay, so what we're going to do is we're going to apply your KCL. Okay, so we are going to apply KCL to each node expressing branch currents, okay, in terms of node voltages. So actually we are adding, or we are subtracting your currents in a node. So that is whenever a current enters or leave a node, so we have there if it enters, it's a positive. If it leaves, it's a negative. However, we are going to represent those branch currents by their nodal voltages. Okay, so later on I will be explaining that. And then after that, okay, so after selecting a reference node and after assigning voltages VA, VB, VC, etc. to the remaining nodes, and then after applying KCL to each node, expressing a branch, we are now ready to solve the resulting simultaneous equations to obtain unknown node voltages. Okay, so this time we are trying to solve the node voltages, and when we already know the node voltages, then we can determine now your branch currents. Okay, so let us discuss this in steps. Okay, so first step, let us identify our nodes. So in this case, for example, what are the voltages of the 3 nodes A, B, and C? So actually here we have 4 nodes. Okay, so what are those 4 nodes? Okay, so we have here your node A, you have here your node B, and we have here your node C. Okay, so lastly, we have your node 4 here, but this fourth node here will be used as our reference voltage, our reference node. Okay, so what are the voltages of the 3 nodes? So what are those 3 nodes that we have? We have here node A, node B, and node C. Okay, so how are we going to determine the voltages of each nodes? So as you can see, your node A here is directly connected to our 6 volts source here, and with respect to our reference node. So this is very easy to analyze. So this is very easy to say that our VA, so let us call our node A voltage here. So let us call that VA as equal to 6 volts. Okay, so because where is your point A located? So it is located in this one together with our ground here, which is our reference node. So therefore, what can you see there? So you can see the source, which is 6 volts. So therefore, we can easily say that VA is equal to 6 volts. Okay, so where is VB this time? So VB here is located at this junction, okay, or at this point with respect to our reference point here. So therefore, VB here, we do not know yet its value. So therefore, this is our unknown. Okay, so this is our unknown, and yet we have to solve for this VB first. And then we have your VC. So what is your VC? So where is VC connected? VC is connected at your positive 12 volts here and with respect to our reference node or the ground. So as you can see, this is very, very clear that our VC here is equivalent to 12 volts. So among our 3 nodes here, we only have one unknown, which is our VB. So in this type of problems, we are trying to solve, in this type of circuit, we are trying to solve for VB. Okay, so what's next? So we have to write our equations for the branch currents. Okay, so in nodal analysis, we usually write the branch currents. Okay, so directly in terms of the node voltages and the branch currents, branch resistances. So how do we write current? So current is written as voltage divided by our resistance. So the resistance that is connected to that specific branch. Okay, so care must be taken in keeping the polarity correct. Okay, so you can make problems a little easier but by arbitrarily assuming current which leaves each node. So for example, we are trying to solve for node B, so we're going to assign all of the currents at node B to be leaving. So therefore, they are all additive. Okay, so although there is no problem if you assign, for example, this current I1 here, which is entering, and this is entering, and this is leaving. However, it is suggested, okay, so it is suggested that we can arbitrarily assume current leaves each that following node. So therefore, all of the currents are leaving, so therefore we can make them all additive. Okay, so this simplifies, when we do that, this simplifies writing the resulting equations and prevents polarity errors. There will be no problem with the negative sign. So for example, you have computed for a negative sign. Actually, that is not a problem. That only means that we have to reverse the polarity of the assumed current direction. Okay, so for uniformity, let us just assume that when we are talking about a certain node, okay, so we are going to assume that all of the currents that are connected in that nodes will be directed or will be leaving out of that specific node. Okay, so how do we write equations for these branch currents here? Okay, so how do we write I1? Okay, so I1 here, so I will be writing our I1 here. So I will just write it here. So where is I1 located? So I1 is between VB and VA. So if we're going to look at the polarity or the direction, so this is the positive where current is entering, and this is negative where current is leaving. Okay, so therefore, with respect to VB and VA, VB is positive with respect to VA. So we can easily write here that your current I1, okay, is written as VB minus VA divided by the resistor, okay, the branch resistance that is connected to it, which is equivalent to 4 ohms. Okay, but previously we said that VA is equal to 6. So we can easily write here that your I1 is equivalent to VB minus 6 all over 4. Okay, so we have written our first current equation. Okay, now let us go to I2. So how do we write your I2 here? So I2 is written as you can see, our branch current 3 is only connected across VB. Okay, so unlike 4 ohms here, it is connected both at node B and node A. However, your 3 ohms resistance here is connected only to at VB with respect to our potential ground. And what is the voltage at your potential ground? So this is equivalent to 0. So we can say that this is VB minus 0 with respect to the potential, which is with respect to the ground, which is equal to 0, divided by the branch current connected to that, which is equivalent to 3 ohms. Okay, or we can rewrite this as VB minus, VB. So let us erase that. So this will become VB all over 3. So that is our I2. Okay? And then let us write our equation for I3. So how do we write your equation for I3? I3 now is equivalent to, so where is I3 being directed? So we have here your current is entering, so this is positive and this is negative. So I3, or the 8 ohms resistance here, is connected at your VB, at your node B and your node C. Okay, wherein VB is positive with respect to node C. So therefore, we can write here VB minus VC divided by the branch resistance, which is equivalent to 8. However, previously, we said that VC is equal to 12 volts. So we can write here VB minus 12 divided by 8. So this is now our 3 branch current equations. Okay, so that is how you write your branch current equations. Okay, so what do we do next? Next is, we're going to substitute into KCL and solve for the unknowns. Okay, so for node B, we are going to assume that all of the currents are leaving our node B. So current out is equivalent to current in. So what are those currents that are entering our node B? So we have there your, so leaving point B rather. So we have here your I1 plus your I2 plus I3. So since no current is entering, so this is just equivalent to 0. So it is also referred to, so ma'am, if it is leaving, it should be negative. So you can just write negative, negative, negative is equal to 0. Then we can interchange. So we can, that is just the same, okay? So the point here is they are all of the same direction. So therefore, we can simply add all of them. Okay, so therefore, we have established our KCL, which is I1 plus I2 plus I3 is equal to 0. So what do we do now? We are going to substitute what we have written a while ago. Okay, so from the previous slides, we're just going to substitute these currents into its equivalent nodal voltages equations. So what are those? So for example, what is I1? Okay, so I1 is equivalent to VB minus 6 all over 4. Okay, plus, but what is I2? I2 is equivalent to VB all over 3. And what is I3? So this is plus VB minus 12, plus 12, minus 12. So minus 12 all over 8 is equal to 0. So what do we have here, class? So we have here one equation with one unknown, and our one unknown is your VB. Okay, so we have established, so previously in our analysis using your Kirchhoff's laws, you have 3 unknowns here. For example, you have your I1, I2, and I3. So therefore, we will be needing 3 equations. So if we're going to solve this same problem, same circuit using the mesh analysis, as you can see, we have 2 meshes here. Therefore, we have to solve for 2 simultaneous equations. But look, if we're going to solve this using nodal analysis, we can just solve for your I1, I2, and I3 using one equation only. Because in this equation, you only have one unknown, which is your VB. So once your VB is solved, we can easily solve for I1, I2, and I3. So those are the three, those are the comparison, okay, from the previous topics that we have discussed. So if we're going to make use of the Kirchhoff's laws, we will be needing three equations because you have three unknowns, okay? So if we will be using mesh analysis, you will be using two equations because you have two meshes here. But, okay, if you're going to make use of nodal analysis, you just need one equation, okay? Because once you solve for VB here, everything else will follow. Because all you have to do is to substitute your values for VB and you can solve for I1, your I2, and your I3. Okay? And then the last, okay, so we're going to solve for the unknowns. Okay? So what are the unknowns here? Actually, we only have one unknown, which is your VB. Okay, so rewriting now our equation a while ago. So we have here VB. So we have VB minus VA, which is equivalent to 6 all over 4 plus, okay, so we have VB all over 3 plus we have VB minus VC, which is equivalent to 12 all over 8, and that is equal to 0. So we only have one unknown here, so solving these equations simultaneously, so that will be that means you're going to solve for VB here. Okay, so see, we only need one equation to solve for these three unknown currents. So if you're going to make use of the Kirchhoff's laws, okay, you will be needing three equations because our unknowns are I1, I2, and I3. If you're going to make use of the mesh analysis, okay, so you will be solving for two simultaneous equations because technically we have two meshes here. But if we're going to make use of nodal analysis, we can solve for these three branch currents here just by having one equation and by solving our node voltage VB. So what is our VB here? So solving this simultaneously now, solving this equation with one unknown, VB here is equivalent to 4.23 volts. So that is equivalent to 4.23 volts. Okay, so by doing that, okay, so by doing that, we can now solve for each of the different currents here. So what do we have for I1 here? I1 now is equivalent to 4.23 minus 6 all over 4. So from by looking at this by looking at your numerator, we can see that the answer here is negative. So what do we mean by negative? Negative sign there just signifies that our assumption for the direction of I1 is incorrect. So we just have to reverse the polarity of your current direction here. Okay, so if we're going to, but the numerical value there is correct. So if we're going to solve for I2 here, this is equivalent to VB, okay, so divided by 3, so or that is equivalent to 4.23 divided by 3. So as you can see, we will be having a positive answer here. So therefore, your I2 here has the correct polarity or direction. Okay, and lastly, we can solve for I3, and I3 is VB, which is 4.23 minus 12 all over 8. So obviously, we will be having a negative answer again here. So what does that mean? So that means that our assumed polarity for I3 here is incorrect. So therefore, the direction for I3 must have been in this direction. But the numerical value is correct. Okay, so that's our nodal analysis. Pero hindi mawawala yung...
Hindi, susunod-sunod din
Okay, so let's have an additional example here. Okay, so we have here our problem. We have to solve for voltage VB. Okay, so what do we have here? So we have here our VA again. Okay, so let's have our VA here. So what is your VA? Again, just like a while ago, let's like our previous example, our VA here is equivalent to 15 volts. Okay, so we have here your VB. So what is our VB here? This is our unknown. Okay, so we have to solve for this VB. Okay, but what is the difference between our previous example from this example here? So you can see that our VB here and our VC here are in parallel. Okay, so what is the voltage when we have parallel circuit? So we say that in parallel circuit, we have equal voltages. So in this problem, we can say that your VB is equal to your VC. Okay, so what do we do next? Okay, so we let us establish your current equations. Okay, so we say that we will be assuming that all currents will be leaving this point B here or node B. So let us assume this is your I1. Let us assume that this is our I2, and let us assume that this is our I3. Okay. So, we have here our three currents, okay? So, all of them leaving our node B. So, let us write now our current equation I1. So, what will be our current equation for I1? So, that is VB minus VA all over 5. Okay, so that is your I1. Or we can say that we have VB minus 15 all over 5. Okay, and then let us write our equation for I2. So since I2 is connected to the ground, reference to the ground, so we can say that our I2 here is equivalent to VB all over 4. Okay, so that is VB minus 0 all over 4, or simply let us write that as VB all over 4. Okay, so how do we write our I3? So same. So instead of writing VC, so we will just express your VC with respect to VB because they are just equal. So we can just write here VB minus 0 again all over 8, or simply VB all over 8. Okay, so upon establishing these three current equations, we are now ready to write our KCL. So what is our KCL here? So our KCL there is equivalent to I1 plus I2 plus I3 is equal to 0. Okay, so rewriting that here in our equation, so that is VB minus 15 all over 5 plus, we have here VB all over 4 plus VB all over 8 is equal to 0. Again, we have one equation having only one unknown, and we can easily solve for VB. Okay, so the answer for VB here is 5.217 volts. So once we know VB, you can easily solve for I1, you can easily solve for I2, and you can easily solve for I3 just by substituting the value 5.217. Okay, so when your answer is positive, that means our assumed polarity is correct. But when your answer is negative, all you have to do is to reverse the polarity of your answer. Okay, so that is our first example. So, let's make, the nodal analysis is very simple. Okay, so let us, how about, okay, so what about if we have here a change in polarity? Okay, so the polarity of the voltage supplies changes how you write your equations. Okay, so you notice here the inverted polarity. So in our previous example, in our introduction, this is plus and minus. So what will happen if this is minus? minus plus. Okay, so the same step. Okay, so how do we write your I1, for example? So we can write your I1 as, so we can write your I1 there as VB, okay, minus, but what is VA? That is 6, okay, divided by 4, okay? So we can write your I2, okay? So what is our I2 there? So our I2 there is equivalent to VB all over 2, okay? So what will be the change if we are going to have an inverted power supply? Okay, so for I3, we can write I3 here as VB, okay, minus VC all over 8. Okay, so since this is inverted, okay, so this is negative with respect to our reference, we will just be writing here VB minus. But what is our VC? So this is negative with respect to our ground here, diba? So we have here minus 8. Okay, so what will happen? Okay, this is divided by 8. So this will just become VB plus 8 all over 8. Okay, so this will just become positive instead of negative. So all you have kindly take notice of the inverted supply. So once you have this already, you can just easily solve for VB. And then upon knowing VB, you can solve for your I1, you can solve for your I2, and you can solve for your I3. Okay? Okay, so this is our next example. Okay, so it says here, how many nodes in the circuit below have unknown voltages? So how many unknown voltages do we have here? So if you will be looking at the nodes, we have here node VA, VB, VC, and VD. However, class, if you're going to notice here, okay, that your node VC here is in parallel with your node VD here. And our VD with respect to our ground is directly connected at 10 volts. So that therefore, VD is equivalent to 10 volts. While since your C is in parallel with VD, we can easily say that your VC is likewise equivalent to 10 volts. Okay, so in this case, we only have one unknown voltages, and that is our node V, node B rather. Okay, so also in this problem, we are determined to solve for our unknown current. So this is the direction of our unknown current here. Okay, so let us now look at our given. Okay, so what is our VA here? Our VA here is equivalent to 5 volts. Okay, so our VB here is unknown. Okay, so our VB here is unknown. Our VC here, okay, our VC here is also equal to our VD, and that is also equal to 10 volts. Okay, so let us now write our current equations. Okay, so let us assign our current here in our node B. So let us assume that all of the currents will be leaving our node B. So let us call this our I1, let us call this our I2, and let us call this our I3. Okay, so let us establish our equation for I1. So I1 here is equivalent to VB minus VA. But what is our VA? Our VA is equal to 5 divided by the branch resistance, which is equivalent to 15. Okay, so what is our I2? Our I2 here is equivalent to VB minus 0, okay, divide by our branch current, which is equivalent to 20. Okay, and finally, we have here our I3, which is equivalent to VB minus VC all over 30. Okay, so our I3 here is equivalent to VB minus 10 all over 30. Okay, so 8 here is not included because the current that will flow here has nothing to do with node B already. So we will not include the current which will flow across your 8 ohms. And then we're going to establish your KCL. So what is our KCL here? Okay, so our KCL here is I1 plus I2 plus I3 is equal to 0. Okay, so rewriting our current equations, we have here VB minus 5 all over 15 plus VB all over 20 plus VB minus 10 all over 30 is equal to 0. So we only have here one equation with one unknown, and that is our VB. So using your mathematical, using your calculator here or your math here, we can easily solve for VB. And our VB here, class, is equivalent to 4.94 volts. Okay, so knowing VB, we can easily solve for our unknown, which is this one. Okay, so our current here is related with I3. So if we know I3, we can solve for or we can define our current unknown here. So we can solve for I3 just by substituting. Okay, so I3 is equivalent to VB, which is 4.94 minus 10 divided by 30. So we can solve for I3. So using your calculators, I3 is equivalent to 185 milliamperes. Okay. However, by looking at the numerator, we can have here a negative answer. So our I unknown here is equivalent to I3. They both flow here at 30 ohm resistor, but they are of opposite direction. So if we're going to solve for your I unknown now, so your I unknown is equal to negative I3. So why negative I3? Because they are of opposite direction. So therefore that is negative 185 milliamperes. So that means that your I unknown is positive 185 milliamperes. So the proper polarity or the proper direction for the 30 ohm resistor is equivalent to 185 milliamperes flowing from node C to node number B. Okay, so that is our example number 2. Let us go to example number 3. Okay, so in here, we are to find the voltage at node C, okay, and the unknown current. So I unknown. So this time, we're going to look at our node C. So first, let us identify the nodes A, B, C, and D, okay, and then we're going to draw your currents, okay, so that will be leaving point C so that we have a uniform computations, and then later on we're going to write our equations. Okay, so we have here what is our VA here. Okay, so since we are finding the voltage at node C, so let us call our currents that are connected at node C. Okay, so let us have here your I1. So let us call this I1 flowing in this direction. Let us call this your I2, and let us call this your I3. All leaving our node C. Okay, so let us identify our nodes. Okay, so let us now write our equations. Okay, what is our equation for I1? Our equation for I1 is equivalent to VC minus, okay, so this is minus VB all over 3. Okay, so however, as you're going to look at your VB is in parallel with VA, okay? And VA has a direct voltage source connected to it, which is equivalent to 24 volts. So therefore, the voltage across your VB is equivalent to 24 volts. So therefore, we can rewrite here your I1 as VC minus 24 divided by 3. Okay, so how about I2? So how do we write I2? I2 is directly connected at your node C. So this is simply VC all over 2. Okay, and then let us write our I3. So what is our I3? We have VC minus VD all over 8, okay? But VD has a voltage source which is equal to 12 volts. However, the 12 volts is what? The 12 volts is in a reverse direction or polarity. So therefore, instead of having minus VD, it will become positive VD. So in rewriting that will give you VC minus VD, but VD is negative 12 all over 8. So rewriting that, we have VC plus 12 divided by 8. Okay, so therefore these are now our equations. So we are now going to write your KCL. So what is our KCL there? So that is I1, all currents leaving our point C. So that is plus I2 plus I3 is equal to 0. So what is our I1? I1 is VC minus 24 all over 3. Okay, so we have plus, what is our I2? I2 is VC all over 2 plus, what is our I3? I3 is VC plus 12 all over 8 is equal to 0. Okay, so we only have here one equation having one unknown, so we can easily solve for VC. Okay, so what is our VC there? VC using your calculator, so kindly solve. The answer there is 5.14 volts. Okay, so using your VC, you can easily solve for I1, I2, and I3. However, we are not required to solve for those three. We are only asked to solve for the I unknown. Okay, however, the I unknown is what? Is also happens to be your I1. And this time, they are of the same direction. So whatever our answer for I1 here, it will be our I unknown, both in the polarity, both in the direction and in the magnitude. Okay, so how do we solve for I1 now? All we have to do is to substitute our values. So our I1 is VC, which is 5.14 minus 24 divide by 3. Okay, so we solve for I1, which is also equal to our I unknown, and that is equivalent to negative 4.715. 4.715 amperes. Okay, so the 4.715 is the correct magnitude for that, the same value for that, but we have the wrong assumption. So your I here should be entering node C and not leaving node C. But the amplitude here or the magnitude here, it is the same. Okay, so that is our example number 3. Okay, so what happens now if we have current sources? Okay, so from our previous examples, all we have are voltage sources. Okay, so what happens to nodal analysis if we have current sources? Actually, a current source makes the equation simpler. Okay, so it will make your computations easier since now you know what the branch current is. Okay, but always remember to pay attention to polarity. Okay, so what do we have here now? Okay, so in here, this is very simple because as you can see, I1, okay, and your 3 amperes here. So as you can see, your 3 amperes here will be flowing across your 5 ohm resistor, which happens to be your current I1 here also flows along your 5 ohm resistor here. So what can we conclude here? So this is very simple. We can easily say that our I1 here is simply equal to 3 amperes, but look at their polarity, look at their direction, they opposes direction, so therefore all we have to do is to write a negative sign here. So therefore we have there your I1 is already equivalent to 3 amperes. So we already have a value for our I1. Okay, so for our I2 it will be the same. Okay, so for our I2, that is equivalent to VB, okay, divided by 4. Okay, like in our previous examples. Okay, and then in our I3 here, okay, so for our I3 here, since this is already zero potential again here, so current I3 will be flowing across your 12 ohms here. So we can write here your I3 is equivalent to VB, so this is also connected to VB. Okay, so that is VB minus 0 again. So this is your potential here. So this is considered as only one node, okay, because we don't have any resistor here. So this is considered only as one node. So that will become VB all over 12. Okay, so therefore, if you're going to write your KCL there, so your KCL there is again I1 plus I2 plus I3 is equal to 0. So rewriting that, that will become minus 3 plus VB over 4 plus VB all over 12 is equal to 0. Again, we only have here one equation with one unknown. So you can easily solve for your VB. Okay, so that what happens if you have a current source. Okay, so that makes your circuit, that makes your solution a lot easier. Okay, let's have our fourth example here. We have here solve for node voltage VB. Okay, so as we have did a while ago. Okay, so what do we have here? We have here your I1. Okay, so let us all of the currents are drawn leaving node B. Okay, so we have here I1. So look at I1 and look at your 3 amperes there. So they are both flowing across your 4 ohms. However, they are of different directions. So we can easily conclude that your I1 here is equivalent to negative 3 amperes. Okay, and then let us write our equation for I2. Our I2 is equivalent to VB all over 3. Okay, and then let us write our equation for I3. So this is already easy for you. So this is very familiar now. So we have here VB minus VC. Okay, but what is VC? VC is equivalent to 12 divided by 8. Okay, so writing our KCL now. So what is our KCL here? This is I1 plus I2 plus I3 is equal to 0. Okay, so therefore, we can now solve our equation. So we have here negative 3 plus VB all over 3 plus VB minus 12 all over 8 is equal to 0. One equation with only one unknown, which is our VB, we can easily solve for VB. And for here, your VB is equal to 9.81 volts. Okay, so I hope you are trying to solve this using your calculators. Okay, so how about solving multiple equations? Okay, so for example, in this type of problem here, we have here writing our branch currents equations which will yield into two unknowns. Okay, so what do we mean by when we have two unknowns? That means we also have to have two different equations. Okay, so where can we have our two different equations here? So we can have our two different equations here at node A here and at node B here. Okay, so what is our equation? What equation can we formulate at node A? So let us write here at node A. So what are the currents? Okay, so let us assume our currents leaving our node A. So let us call this your I1, for example, and this is, let us call this our I2. Okay, so from this we can say that we have three currents here at node A. Okay, so we have leaving node A, but this is entering, so let us assume that to be negative since it is entering. So let us assume all of the currents leaving to be the one which is positive. Okay, so we have here -3, and then we have VA all over 6. Okay, then we have plus. Okay, so we have VA minus VB all over 5 is equal to 0. So we have two unknowns. Okay, so we don't know VA and also we don't know VB. Okay, so we cannot solve this yet. So we need another equation. Okay, where are we going to get that equation? So we're going to get that equation at node B. Okay, so how do we write our node B equation? So assuming all of the currents again leaving point B. Okay, so we have here your VB. Let us call this your next I2. Okay, so let us call this your I3. Okay, and then let us call this let us say this is your I4. Okay, so what do we have there? So we have here VA or VB minus VA all over 5. So a while ago, it is VA minus VB because it is with respect to node A. So this time, it is VB minus VA because it is now with respect to point B. Okay, so we have here plus. We have VB, okay, VB all over 8. Okay, and then we have plus. We have VB minus. Okay, so supposedly it is C here, but since this is connected to a voltage source, so therefore this is equivalent to 12. But since this is negative, this is this is negative 12. Okay, divide by 6 is equal to 0. So rewriting, we have VB minus VA all over 5 plus VB all over 8 plus VB plus 12 all over 6 is equal to 0. So we have two unknowns again. We have VA and VB. Okay, so this is our equation number 1 and this is our equation number 2. So in this case, although we have two unknowns, it is not a problem because we also have two equations. So all you have to do is to solve these two equations simultaneously so that you can solve for our VA and VB. Okay, so depending on what technique you are using, so it's either by elimination, by substitution, okay, or by determinants, so you can easily solve for the value. Okay, so try it using your calculators. I will give you the answer. See if you can if you can get these values. Okay, so VA here is 7.66 volts and VB is negative 0.951 volts. So what do we mean by the negative 0.951? So therefore, the polarity of VB there is reversed. Okay, so it should be reversed in polarity, but the numerical value, it is correct. Okay, so that is how you do, or that is how you're going to solve this nodal analysis if you have multiple equations. Okay, so depending on the number of nodes, of course, the more nodes you have, the more equations, or the more nodal voltage that you are trying to solve. Okay, let's have another example here. We have here solve for your I unknown. Okay, but before we go to that, let us first try to solve our node problems. Okay, or nodal. Let us formulate our nodal equations here. So we have here our node at node A. Okay, so because our I unknown is concentrated at both A and B, so we can have our equations here around node A and node B. So at node A, let us first assume our direction, which are all leaving node A. So let us call this our I1. Let us call this our I2. Okay? So at node A, so let us establish our equation for node A. Since our 3 amperes here leaves node A, so we will be treating this as positive also. Unlike a while ago, since it is entering, we had a negative sign for that. So since we are assuming all leaving currents to be positive and 3 amperes is leaving node A, so we will be assuming that this is positive. So we have here 3, okay, plus we have VA all over 2, okay, plus we have VB minus VA minus VB all over 4 is equal to 0. So that is your node 1. Okay? So let us go to node B. So this is our node B. So at node B, let's use different color. So at node B, let us assume that all currents leave node B. So that let us call this your I2. Okay, let us call this your I3 and let us call this our I4. Okay, so we have here what is I2? I2 is VB minus VA all over 4. Okay, and then we have plus, we have here your VB all over 6. Okay, we have here plus VB minus VC. Okay, but what is VC? As you can see, your VC is in parallel with our 16 volts here. So therefore, the voltage across your VC is equivalent to the voltage across your VD, which is 16. So we have here minus 16 all over 7 is equal to 0. Okay? So we have here two equations with one unknown. So what is two equations with two unknowns? So what are our unknowns? We do not know VA and we do not know VB. We do not know VA and we do not know VB. But we have two equations. We have equation number 1 from node A and equation number 2 from node B. So solving these two equations simultaneously, we can solve for VA and VB. Okay, so try solving that. So I will be giving you the answer if you will be getting the same answer. So VA is equivalent to negative 3.1 volts and VB is equivalent to 2.7 volts. Okay, so what are we trying to solve for is our I unknown. Okay, so by looking at the two values, we can say that VB is positive or more positive, okay, in with respect to our VA, which is negative. Okay, so therefore, what are we going to follow? We are going to follow the direction wherein your VB is our is positive, which is our node B. Okay, so to solve for your I unknown, So that is equivalent to VB. Since VB is more positive with respect to VA, so that is a minus VA divided by 4. Okay, so we have here 2.7 minus negative 3.1 divided by 4. So we will be having a value which is 1.45 amperes. Okay, because if we do the opposite side, that will give you a negative answer. So therefore, we will be following the node which is more positive than the other node. Okay, so that is how you solve nodal equations with multiple unknowns, okay, or with 2 unknowns. It is also possible if you have 3 unknowns, but you have to remember that you have to have 3 different equations, okay? So if you're going to make use of Kirchhoff's laws here, you have so many branch currents. So how many branch currents do you have there? So you have here 1, 2, 3, 4, and 5. So you will be having 5 branch currents. So you will be needing 5 different equations. So for mesh analysis, you have 4 meshes there. So 1, 2, 3, and 4. So that means you will be needing 4 different equations to solve for those different mesh currents. Okay, but if we're going to make use of nodal analysis, we have only 3 nodes here, so 3 nodes minus 1, so that will only have, that means 2 different equations only. So you can solve this using 2 different equations. So those are the differences between when you use the Kirchhoff's laws, when you use the mesh analysis, and when you use the nodal analysis. So actually there is you really have to analyze in a certain circuit what will be the best approach, what will be the best solution for that specific circuit. So the best approach will be the one which you will be needing a fewer equations so that you can solve for the unknowns in that specific circuit. Okay? Okay, so you remember in mesh analysis, we have a super mesh. So that is every time you have a current source between 2 meshes. Okay, so in this case, we have a super node. So what is a super node? So super node happens whenever you have a voltage source between 2 nodes. Okay, so super mesh when you have a current source between 2 meshes. So voltage source between 2 nodes means we have a super node. So just like here, okay, so just like here, class, we have a 22 volts here, voltage source between V2 here and V3 here. So we're going to treat your treat node 2, node 3, and the 22 volts together as a super node, okay? And then you're going to apply KCL to both nodes, okay? KCL to both V2 and V3, or node 2 and node 3, okay? At once. So region of enclosed, look at this region of enclosed dotted lines, okay? So we're going to treat this as one node. Okay, so we're going to say that this entire portion here, so this entire portion here is a certain node. Okay, so leaving node 2 is 0, and the total current leaving node 3 is equivalent to 0. So we are going to treat whenever you have a voltage source between two nodes, you're going to treat them as a super node. So how are you going to apply that? Okay, so let's try solving problem with a super node. Okay, so we have here a super node. So why do we have here a super node? Look at here, because between point A or node A and node B, there lies a voltage source there, which is 12 volts. Okay, so how are we going to treat that? I will be showing you 2 different approach. Okay, so one without using the super node, and then another with using the super node. And let us see if that if we make use of the super node approach, it will be a lot more easier. Okay, so first is without using a super node. So what we're going to do is we're going to look at our node A and node B here. Okay, so we will be analyzing the circuit using both node A and node B here. Okay, so for node A, we will assume that all currents are leaving node A. So this one. So let us call this your I2. Let us call that your I2. And let us call this your I3. Okay? So we can say that your I1, okay, I1 is equivalent to VA all over 6. Okay? And your I3, let us call this your I3, is equivalent to VB. Okay, I3 is VB all over 3. Okay, because this is directly connected sa ground. So, how about I2? Okay, so if we're going to look at I2, I2 is VB, VA minus VB. We don't have any resistor in between. So, therefore, the resistance there is equal to 0. Okay, look, this is undefined because we have here a denominator which is equivalent to 0. So, since we cannot solve for this, we can just assume this to be equal to x. Let us assume this to be equal to x. So we're trying to solve without using the super node yet, okay? So let us just call that x. Now, let us go to node A. What do we have in node A? So since this current is entering and not leaving node A, we're going to treat this as negative. Okay, so we have here 1.5 since it is entering. That is equal to the two current that is both flowing away from node A. And that is what? That is your I1, okay, which is VA all over 6 plus, that is your I2. So since we have here your I2 which is equivalent to x, so let us just write here is plus x. Okay? So let us now go to node B. Okay, so look at node B. So let us assume this to be in this direction. Okay, so let us assume x to be going away from B, and then we have here your 3.5 here, okay, and then we have here your, okay, so let us not change anymore the direction of our I2. Okay, so what we have here is your I3 and your 3.5 amperes here, both leaving our node B. Okay, so since your I2 is entering your IB, so we will be treating that as negative. So at node B, we have your I2, which is equivalent to x, okay, which is equivalent to 3.5, both leaving your point B or your node B, plus I3. But what is I3? I3 is VB all over 3. So this is your node B. Okay, so we have two equations coming from node A and node B. Now, we can combine, okay, we can combine these two equations because we have an x here to eliminate the value of x. So we can substitute the value of x in our first equation. So this will become 1.5 is equal to VA all over 6 plus x. But what is x? X is equivalent to 3.5 plus VB all over 3. Okay, so this is equivalent to 1.5 equal to VA all over 6 plus 3.5 plus VB all over 3. So we can transpose your 3.5 here. So we will be having minus 2 is equal to VA all over 6 plus VB all over 3. So we have here your equation number 1. We cannot solve for this equation for A and B here because we have two unknowns, which is VA and VB, and we only have one equation. So where are we going to get our second equation? Our second equation will be coming from this branch here. Okay, as you can see, we have here, since B is positive with respect to A, we can have here your VB minus VA is equal to 12. So this is now your second equation. Okay? So you have two equations with two unknowns. You can easily solve for VA and VB. So that is when you do not make use of a supernode. So you assign an x, okay, an x variable, and then you try to substitute that x variable in terms of either VA or VB. So what do we do if we apply the supernode? So if you apply the supernode, I will be using another color here. I will be treating this as an entire node. So I will be treating this as entire node. Okay? So if that is an entire node, I will just have to see what are the currents entering and what are the currents leaving at that specific nodes. Okay? So first, what is the current? So this is using the supernode. This is using the supernode. So as you can see, your 1.5 enters that node. So we have here positive 1.5. Okay? Your I1 so we have here 1.5 that enters your node here. Your I1 leaves, so that is minus I1. Okay? Your 3.5 leaves, so that's minus 3.5. And your I3 leaves, so that is minus I3 is equal to 0. So as simple as that. And then you substitute. So what do we have here? So we have here 1.5 minus, this is VA over 6 minus 3.5 minus VB over 3 is equal to 0. Right away, we got this equation, which is very similar to this equation because this is 1.5 minus 3.5, so that will also give you negative 2. But we didn't need to get equation of node A and node B anymore. So if we made this a supernode, we can right away go at this specific equation here. Okay? And then finally, this will be your equation 1 and your equation 2 is the same. This is still your equation number 2. So that is the difference if you're going to make use of the long method or if you're going to make use of the supernode method. So what is the supernode method? Whenever there are two nodes with a voltage source in between them, all you have to do is to make that specific branch a node. Okay? And then just look at the currents leaving and entering that specific node. Therefore, you can formulate your equation. Okay? So that is our topic about nodal analysis. Okay? Thank you very much and God bless.